Recording is rolling. It's Friday, October 10th. So some general announcements. There's of course these meetings going on right now. So if you're bits of class is one of these, of course I'm making a recording. All right, so I'll post this. Okay, yeah, okay. Yeah, there's picture retakes going on. So if you do a picture retake at some point, that's right. Okay, so yesterday on Google Classroom, I posted a flyer about Homecoming Spirit Week. Yeah, it looks like this. Here, I'll scroll through it real fast. So this is not next week, but it's the week after. It's starting with Monday the 20th. Right, we've got these things going on. So again, this is uploaded to Google Classroom. You guys can download it, get a closer look at that. Right, so that's up there for you guys. Right then, right, dynamics quiz. Right, so here's top scientist for dynamics quiz. So awesome job if you made the list. Right, so it's still the two quizzes not turned in yet, so I haven't got that back to you guys. You can eventually do quiz corrections. I'm just going to put the quiz corrections on quarter two. The quiz corrections on quarter two. All right, let's look at the lab you guys have been doing for the last few days. Right, is this right here. So I want to talk about the lab write-ups, because you guys remember for AP style, there's that 5-part write-up they want you guys to do. And here, let me zoom out, go back to the beginning. Right. It's always the same format.
Yeah, but you like these. I think we did more. It's like a
All right, and I did help you guys get a start on this. So the master question here is, what's the relationship among, say, like the hanging weight, which provided the tension? So you could have said tension in this case, the same value. The swinging mass, the radius of that circle is going around, and the speed or tangential velocity. Right. So you have 4 variables. Okay. Now you guys had to narrow it down to 1 of 3 experiments. Everybody was related to everything ultimately to be squared is how we do this. Right? But I wanted to debrief this with you guys because some of you guys I think understood what was going on, and you had really nice looking lab write-ups. Some of you guys were really close. And then there were a bunch of students who like missed a lot of critical details in the write-up. So here I'll go through, here I'm going to just hone in on this one right here. Okay. So well, sorry, I got weird projection issue. All right, here I'm just going to go through this last column, the left column. Let's say you wanted to say radius is your independent variable. So you're leaving the canisters as they are. The swing mass is the same all the way through. The hanging weight's the same all the way through. Tension's the same. Okay. So you're changing the radius. And I want to know, how does that affect the speed? And so you'd have this independent variable. The speed would be the dependent variable. And then the 2 canisters, the mass and the weight would be the controls. Right? Just like that. Okay. So that was your question. Measuring tools. So I told everybody the measuring tools, and these are the 3 tools that you guys use. Use a ruler, stopwatch, and a scale. Or maybe you can say meter stick, stopwatch, and triple to be balanced. That's okay. Something like that. Okay. And I also gave everybody the first step of the procedure. But guys, this was not the whole procedure. This was just basic setup. Is okay, string through plastic tube, got secure the safety buckets to each end, whirl the mass in a horizontal circle so that the weight of the other bucket provides the tension there for the force to hold it in, say, dynamic equilibrium. Okay. So if an AP grader assigns you this particular experiment and they see that setup, think, okay, right, they know how to put it together. But that, guys, that's not the whole procedure. That's just the setup. That's just how you set it up. Right. So again, these next few steps, about half of you guys got these next few steps, and like all these, and about half of you guys just totally neglected to mention. Right? Like, guys, every measuring tool that you mention up here, you have to mention what variable you're measuring with it. So you have to say, well, I want to measure the mass of the swing canister and mass of the hang canister with using the scale or triple B balance. I'm going to use the meter stick or ruler to measure the radius of that circle. Right? And use the stopwatch to time 10 revolutions divided by 10 to get the time period. Right? There's the use of the stopwatch right there. Right? You have to spell out for an AP grader, okay, I'm using this tool to measure this variable with these units, something like that. Right? Right. And then how about the speed, right? Like, guys, everybody's question was relating something to the speed or the speed to something. What's the relationship between, in this case, the radius and the speed, right? And about half of you guys said, oh, yeah, well, you'd have to get the speed by doing 2 pi r divided by t, right? And about half of you guys just neglected to mention that at all, right? So, yeah, you have to have some way to get the speed, right? Because otherwise, how do you know the speed? How do you make graphs, right? And then the way I was leading you guys through is everybody did square the speed, so we could make graphs of speed squared versus something, and then link everything together. Oh, hey, how about multiple trials? Multiple trials. Right, no, you may not have had time to do this, but ideally what you would do is say, like, I suppose you had radius as the independent variable, like this one. You could do 30 centimeters radius and then run 3 trials of that and take the average time for that and get an average speed, right? And then change the radius to say 50 centimeters and run 3 trials of those and take an average and so on, right? And so even if you didn't have time to do that in the lab, in the class periods, right, at least you'd want to write that down on paper, right? So that if this was a free response question, you'd say multiple trials. Guys, that's always a point. That is always a point on the exam. Is something about multiple trials to reduce experimental uncertainty. Okay? And then, how about identifying what was your independent variable and dependent variable and controls? So if you said, oh, repeat the previous few steps for various values of R, there I just identified independent variable, boom. Keeping the mass and the weight constant, there's my controls, boom, boom. Yeah. And then if I'm solving for speed and speed squared, that would be the dependent variable. All right, so there, just real short statement, I identified what's independent, dependent, and controlled. Right, so you want to communicate that to whoever's reading your paper. Okay. All right, and then the analysis, of course, everybody got it because that was just the graphs and put all the graphs together. So analysis, you're good. Okay. And then the conclusion. Now, there are 3 experimental conclusions. So like this one is v squared is proportional to r, and we brought that together to make one giant math equation, but we needed everybody's data to do that. Right? Because word on this, notice v squared was directly proportional to r. That's if you make a graph of v squared on one axis and the radius on the other axis, you're changing the radial size, get lots of different radial sizes, different corresponding speed and speed squared. Okay? All those points line up in a straight line. That's what directly proportional means. So some of you guys wrote like, oh, there's a parabolic relationship. It's like, okay, they're true, between the speed and the radius, but that's a little bit ambiguous because which variable is being squared? You say, oh, between the speed and the radius, there's a parabolic relationship. That doesn't exactly tell you. Is the speed squared? Is the radius squared? Right? It's kind of ambiguous. So you want to spell that out. So you could say this. Actually, you could just write this equation. Like that would do it. Right? V squared proportional to r. That proportionality. Or you could spell it out in a sentence. You could say the speed squared is directly proportional to the radius. Boom. For that scenario. Something like that. Right. So you want to spell it out so that whatever AP grader is reading your write-up, they can follow, like, okay, right, I see what the independent and dependent variables are. I see what measuring tool they're using to measure what variable. Right? And I see what they did with the data, right, and how they graph that. Right? And what is actually proportional to what. Right? So I think if you turn in your lab by yesterday, then it's already back in your folder. Right, so if you missed some details, then I made some notes and you can see what's what. Right. All right. So how about rest of today? See how much we got here. Got till well, wait a minute. We got till trying to see the time here. 42. Okay, we got about half an hour or so. About that. All right. So picking up from here because this is again your lab from last few days. We put together. We got this. What I want to do is, I need to get you guys this page right here. Okay, so chapter 6 puzzles. Let me do that. Let me pause this video real fast and hand out this page to you guys. All right, back to recording. So here, hey, look at this picture right here. Does that look pretty much identical to what you've been doing in your lab? That looks like that, doesn't it? You got some math going around. You got another one acting as a weight. Got some radial side, circle. It's in motion. Something like that. Okay. Kind of like that. Right. So take you guys over these puzzles. Now, a lot of these you'll be able to solve just from doing this lab the last few days. Not all the puzzles, because there's some stuff we haven't got over yet, but we're at the end of the week, so I'm gonna close down the week. I think it want to have guys apply this whole week before Saturday. Okay. Right, so there's some warm-up questions here, which probably look a lot like your lab. This one definitely looks a lot like your lab. Okay. So things moving in circles. So we got now on the back side, it gets to universal gravitation. We got planets, we got gravity fields, right? We got orbital periods. Okay. Now I haven't talked about any of that yet, so we're going to say that next week. But what I did in my earlier class is I picked number 20, and we spent a good amount of time doing number 20. You guys see this conical pendulum, which is a lot like your guys' lab, except it's considering 3 dimensions. Okay, you guys see conical pendulum? Okay. So if I sort of put these side by side, kind of like I fit here. Because when you were rolling this around in a circle, was your string actually truly horizontal? No, it couldn't be, because this mass up here actually does have some weight, so it pulls down a little bit. So the string can't pull exactly horizontal. It actually pulls a little bit on an angle. Now, for most setups, that small angle would not really throw anything up. If it's like less than 5 degrees, it makes almost no difference. Right? You guys, what's cosine of like 5 degrees? It's like 0.996, right? Something like that. So, I mean, but if you had a heavy mass here, some of you guys actually had some sets that look more like this. Right? So, how would you approach something like that? More like a conical pendulum. So, I'm going to do that one with you guys. We're going to go all through this one, right? And then we'll see where we are. So, look at this conical pendulum here, maybe more realistic. Right? So, you have to think in 3 dimensions. Right? So, the question number 20 on your page, the first thing I want you to do is to draw a free body diagram for this mass that's swinging around in a circle. Circle of constant radius. Right. So go ahead. Here, I'll walk through it with you guys. Number 20. So you have this setup here. I got this ball. Ooh, mass is 0.75 kilograms. 0.75 kilograms. Well, I know what 1 kilogram is. That's your largest lab weight. This is 1 kilogram. So it looks like this ball is about 3/4 of that. The nether here. And see, it's on a string. This tether here, 1.25 meters. So that's a little over 1 meter stick long. Okay. And connected to this pole. Yeah, here, I'll make this a little longer just so my pictures are alive. It's on this pole. And it's going around in the circle. Okay. With some constant radial size. Okay. And they give you some values. So I'll say given. And write some things over here. Okay, so they told you that this length, maybe I'll call this L for length. Length is 1.25 meters. That's the first thing they told you. Right? They told you this angle right here. You guys see this angle from the vertical? They gave that as 35 degrees. 35 degrees. 35 degrees. Okay. They gave you the mass of the ball going around as 0.75 kilograms. Okay. And one more detail that doesn't mattering is the gravity field it's in, which they didn't explicitly mention. But here, what do you guys feel like using for gravity field today? 10? Right. Yeah. 10 meters per second squared. Okay. Right. All right, so let's say those are like the 4 given values. Question A, draw a free body diagram for this tether ball under these conditions. Right? So it does have some tangential velocity, of course, otherwise it would just be hanging straight down. Okay. So maybe I'll label that V, which is not part of the free body diagram, but it does influence the diagram. Right? It has to be in motion. Okay. All right. Now I'm going to pause this video and walk around class and see who can correctly draw the free body diagram for that scenario. All right, we're back recording. So what do you guys come up with? You guys, what's 1 force on this ball? Gravity. Yeah, its own weight. So here, put a big old center mass dot and just draw a vector straight down. And I'll label that mg. Could that be mass times gravity field? Or you could have said this. You could have said F sub g. And you don't have to do both. It's just one or the other. Okay? Guys, what's another force on this ball?
Normal force from the rope.
It's not called normal force. It's called a tension. Tension. Yeah. Guys, normal means perpendicular. It means some surface force. So if you have some object like sitting on a surface, right, there's some upward acting force. Right. That's not what's going on here. Yeah, tension. And guys, which direction does the tension pull? Along the direction of the rope. Yeah. And guys, which force is bigger? Which force has a greater magnitude? The weight down or the tension up and to the right? The tension. Yes. The tension is a greater force. Greater magnitude force. So I'm going to draw this vector a little longer. I'm going to label as F sub T for tension. Okay. Whenever you deal with conical pendulums, I try to avoid capital T for tension because there is also a time period to go around. So it's easy to mix those up. What? Okay, so that's F sub T. Actually, I'm going to shift that down here. F sub T. Like that. Okay. Guys, are there any other significant forces, or is that it? I think that's it. Right? Now I heard I heard a candidate for what about air drag? Which is true, but we're just going to ignore air drag. Okay, so those are the only forces that really matter to us. Okay? Which, by the way, that's also what I got on the poster. Here, let's look at the poster a little bit, because this will help for the next few steps. So I have 2 vectors right here. Okay? Now, could I break this tension into components? Say, well, this tension is partly pulling the ball up. That's this dash right here. And partly pulling the ball in. You see like a right triangle right there? Okay. In fact, if I add these 2 vectors, there's only 2 forces. If I add these tip to tail, or you guys see either way, I get to this brown resultant net force. Yes. Is that? And guys, is this brown resultant net force? Is this truly horizontal?
Yeah.
Yes, it is. Yes, it is. Right. So no single force is straight horizontal, but the net effect is. Yeah. Guys, yeah. Right. And so how can I break this tension into components? Let's do that. Let's do this right here. So this tension is partly pulling up. It's partly pulling across. Here, we get rid of this little left here, right here, to get this out of the way. There we go. So, guys, if you know that this angle right here is 35 degrees from the vertical, and keep in mind, sometimes they might give it to you from the horizontal, so be ready to feel that. But usually, this scenario, they'll give it from the vertical. Okay. Then what is this angle right here? Is this also 35 degrees? Yes, it is. Yes, it is. This is also theta equals 35 degrees from the vertical. Okay. If that's true, then, guys, what is this component right here equal to?
Cosine theta.
Cosine component. You guys like cosine? So take whatever the full force is in the string, which we don't know yet. We don't know the tension force yet. But whatever it is, if you multiply by cosine of 35 degrees, that would represent the vertical component. And then this one right here would be ft times sine of 35 degrees. Okay, because isn't that opposite of my 35 degree angle? Okay. Right. Okay, let's start pulling some numbers. So actually, I bet you guys have known what the weight is. Guys, what is the weight of this ball?
7.5 newtons.
7.5 newtons. 7.5 newtons. Okay, so we have a hard number now. Right. Okay. Guys, see? So impact G 0.75 times 10. So it weighs 7.5 newtons. Got that? All right. Let's go over here. Draw a three-body diagram. Got it. There's just two forces, the weight and the tension. It says apply Newton's second law to calculate the tension in the rope. Now, yes, what is Newton's second law? Newton's second law says what again? F net equals ma. F equals ma, right? So law of inertia is objects going to move in straight lines at constant speed. Second law is F equals ma. Third law is the equal and opposite forces rule. Okay. All right. Now, in this case, I was a little confused when I first read that. So thinking, like, what's the actual application here? Because I know how I would solve it, and this isn't the first thing I would think. Right? But I kind of see the connection. Here, I'll give you guys a hint. Guys, what is the net force? Not overall, not in the x direction, but in the y direction. What if I put a little subscript y here? Guys, what's the net force vertically speaking? 0. 0. Okay. Because this ball is not accelerating up or down. In fact, it's not even moving up or down. Okay. It's only moving horizontally. Okay. So, can you use that to solve for the tension and the rope? Let's see. You know what? Yeah, there's enough information lying around. So I'm going to pause this video and walk around and see who can solve the tension in the rope. All right, so we're going to figure out the tension in the rope. Guys, it falls right out of this right here. Okay, some of the forces in the y. So isn't this tension partially pulling up with an amount equal to the tension force times cosine of 35 degrees? Is that how much it's pulling up? And isn't the weight pulling down? Or I'm going to make this a general theta so I can pop the number later. Okay, minus mg goes to 0. Right here, if this is a general theta right here, this expression will solve all these conical pendulums. And then I could just pop in the values. So I could say tension force we're solving for cosine of 35 degrees minus 7.5 newtons goes to 0 newtons. Okay, you can add this over and divide by cosine. Tension force is 7.5 newtons divided by cosine of 35 degrees. 7.5 on cosine 35. Okay, so the tension force is 9.1558. I'll call it 9.16 at newtons. Okay, it's pretty good right there. You're good. Okay, so you guys get with getting the tension force? Bring this back to the poster because this is on your thumbnail notes. You guys had this. Here, guys, it's this one right here. Isn't this exactly what we just did? Okay. Now, guys, look at this other setup here. There is a sine component of the tension, and isn't that acting as the net force? And what is the net force for this type scenario? mv squared over r. Ooh. Do you think there's enough information we can calculate exactly how fast does this have to be What do you think? Right, you think? I think that's the next question. Let's see if it is. Yeah, calculate the speed of the ball. There it is. Question C. Here, I'll give you guys one hint to get you going. Do you think the radius of the circle matters now? The radius? Okay. Yeah, because NV squared over R. Okay, it has something to do with this radial size. You guys, what is this radial size right here equal to? R equals what? Or what times what? Do you know any lengths at all?
Length of string.
Yes.
Yeah, string length. L times what?
Sine 30.
Yeah, sine V. Angle from the vertical. L sine theta. Yeah. Okay. All right. So you need that. All right. So go ahead. I'm going to pause this video again. So take a couple minutes. Go ahead and solve for the speed. All right. We got recorded back on. Recorded back on. All right. So question we're trying to figure out is what's the speed of this ball, the tangential velocity. Now I did it earlier today, and I also did it just now, and I've been getting speed is 2.24 meters per second. But let me show you guys where that comes from. How to get that. Right, so, I mean, the more important thing is the process. What's the process? Right, so the setup is going to be actually now here's where I would definitely pull out Newton's second law of motion. I think it was MA, and we're looking at all the horizontal. Here's a good picture right here. Okay, so guys, which direction is the net force pulling on this ball? Is it straight towards the center of the circle? Right. Which here, maybe this is a better picture. Goes like that, right? Straight towards the center. Okay. Now that's the net force, which is the combination of both the tension and the weight. And guys, this is a special kind of acceleration. What kind of acceleration are we talking about? Centripetal. That's in contrast to tangential. Guys, the ball's not actually speeding up. It is going at constant speed, but not at constant velocity. Because the speed is the same, but the direction is changing. Yeah, hence centripetal acceleration, which also points to the center of the circle. Right? So, next thing. Guys, what is the net force in terms of the tension in the rope? It'd be F tension times what? Guys, if you're going from this tension to this net force, playing off this angle, is that sine or cosine? Yeah, that's right here. Sine. Yeah. Guys, you guys see how that's opposite of the angle from the vertical? Guys, that's this right here. It's the same thing. Right? Like all the important components are really on this poster, and it's not a lot. I really stripped it down to just what you need. It's this right here. You guys see that? Is that okay? That makes sense, right? All right. Okay, so over here, we're going to say for F net, I'll call that F sine theta, or tension force sine theta, right? And then guys, in place of centripetal, well, for everything on the right side of the equation, what can I write over here? How about the answer to your lab from the last 3 days? M squared over R. Right? Not true? Right. That's okay, right? You guys good with that stuff? Right. And our goal is this V, right? So keeping my eyes on the prize, I should be able to figure out everything else. In fact, we know this tension force, because that was the answer to the last question. That showed up as 9.16 newtons about. Something like that. Okay. But guys, here's the other connection. Guys, what is this radius in terms of the length? Did I do that with you guys? Yeah, remember, you guys remember this right here? L sine theta is equal to R. So in place of this R, can I substitute L sine theta? I can do that, right? Is that okay? Right, you guys follow this? Okay. And now, you know what? I'm just gonna continue with that. And at some point, I got to plug in numbers, but isn't it good to be able to solve it in terms of variables also? Okay. Can you cross multiply the L and sine theta and then divide down the M? So that would look like tension force times sine theta times another sine theta, or you could call it sine theta all being squared if you like, okay, times the length, all divided by the mass, and then the square root. That's what would be equal to the speed. Like that will do it, wouldn't it? You guys see that? Okay. I'm pretty sure I've asked that as a quiz question in the past, or some version of that. Okay. And what do we do? Oh, I think at this point we know everything because they told us theta was 35 degrees. They told us the length is 1.25 meters. They told us the mass is 0.75 kilograms. And they also, yeah, how are we doing on time here? Okay. They also told us, or sorry, we figured out the tension. We figured out the tension right here. Let's that. Okay. So let's put it all together. So V equals the giant square root. I got a 9.16 Newton tension, which we figured out a few minutes ago. I got sine of 35 degrees. In fact, I got two of those, so I'm going to square that term. I got a length of 1.25 meters. And this is all divided by 0.75 kilograms. Yeah. Right, just like that. As long as all that's underneath the radical, that should do it. Right, so calculator time. Okay. And I know what I should get because I've been getting this over and over, 2.24 meters per second. So let's see if that's true. Square root. Right, 9.16. Sine. Open parentheses, let's do sine of 35 degrees and we'll square that. I got a 1.25 over 0.75. Okay, so, oh, there it is. 2.24, and that's meters per second. I got newtons, meters, divided by kilograms, and the square root. Yeah, it works out to meters per second. So that's your tangential velocity. That's the speed of the ball. If you point a radar gun at the ball, that's how fast it says it's going. All right, you guys be able to do that? Sorry. All right, and then last question. As the ball passes one of the players slaps the ball to exert a force in the direction which the ball is moving. Explain why the that angle increases. Right. Well, here I'll just go this one verbally with you guys. Okay. Guys, if it's already going around counterclockwise and you hit it to spin, they go even faster counterclockwise. Isn't the ball speeding up? Speeding up. Okay. And let's see if the ball speeds up, this v increases. Okay. Let's well, what point should we play off here? Okay, if this v increases, okay, yeah, what's increasing or decreasing or not changing in Sato's expression? Okay, guys, would the length of the string change at all?
No.
No. Would the mass of the ball change?
No.
No. Right. But I bet both the tension and the angle both have to increase. Would that be true? Right. So what you could do too is that tension was mg over cosine theta. Let me do that. I'm gonna right here. I'll do some peeking to kind of distinguish it. Okay. That tension force was mg over cosine theta. So this works out as mg over cosine theta. Then I have sine theta being squared here. I have the length all divided by mass. Ooh, guys, the mass. Hey, that's interesting. What happens to the mass of the ball? Here, I got a little side thought here. Okay, suppose we replace this ball with a different ball, like a tennis ball or a baseball, and had it going at the same speed. Would it have the same geometry, conical pendulum with the same radius in it and all? Yeah, because the mass cancels out. It turned out it never actually mattered what the mass of the ball was. It ends up canceling out. Well, it matters to the tension, but not to the speeds and the radius. Okay, so from this point of view, okay. Now, from this point of view, I think it's more obvious. If the speed is increasing, the gravity doesn't change, the length doesn't change, but this theta would have to increase because we got sine squared theta over cosine theta square root. Well, okay, so that's how you can show it mathematically. The angle would have to increase. Okay, that was a little tricky. Okay. All right, so we've got a few minutes left, so I'm going to throw some more ideas on the board for you guys to take off. Okay. You guys remember the other day I broke out this turntable and where'd Roosevelt go? I'm sure he rolled off somewhere. All right, whatever. Okay, so if I give this a spin, right, we're saying, well, yeah, there's this linear speed, like meters per second, right, which is different for both these. But now there's also an angular speed, like turns per time, radians per second. Okay, guys, do both of these have the same turns per time, same radians per second?
Yeah.
Yeah, right? But they have different linear speeds. They both going through speed gates. That's right. So the connection was this one right here. So you could say how far, how fast, and also acceleration in a linear sense. That's what x, v, and a are. Okay. But there's also this angular sense, something to do with radians. So how far is it turned? You can quantify that in radians. or degrees if you like, but it has to be radians to make this connection. Okay. How fast is omega? So that's like radians per second. Okay. What is omega for the entire Earth? Does the Earth have an angular velocity spinning on its axis? Guys, the Earth makes one revolution every how often? It's that one rotation every 24 hours. Yeah. Guys, isn't that omega for Earth? Is one rotation every 24 hours? Now, I'm sure you could quantify that in radians per second, probably some small decimal. Okay. And to go from one to the other, all you have to do is multiply by r. Well, to go from angular to linear, just multiply by r. Okay. So if you're twice as far out, you move twice as far around, and you also move twice as fast. Okay. Now, guys, could you do this? Could you take this omega r and substitute it into this v? This v? Guys, watch this. I'm going to do a little algebra right here. What if I have, okay, I know for a point mass, the terminal force is mv squared over r. But what would it be for a turntable? Like if I have a point on a turntable and give it a spin, how much friction force has to act as the centrifugal force to hold it on? So in place of v, can I replace that with omega r? That's the same thing, right? Omega r, and then square that, and then divide by this r. So that looks like m omega r squared over r. One of those r's goes away. M omega squared r. Okay, so what this is represents, say, a necessary centrifugal force in terms of not linear speed, but angular speed. Isn't that what this omega is right here? Angular speed. And you could quantify that in radians per second. Actually, you would want to quantify that in radians per second to use this. So, you guys know what a O'Neill cylinder is? I think I played you guys a short video the other day from 2001 Space Odyssey. You guys remember seeing one of these in space? It's on the video from the other day. So, you guys think, guys, if this was not rotating at all, would all these people just be floating around in space because there's no significant gravity nearby? But if you give this a spin, they could be walking around and they feel like there's gravity. Now, really, what's going on is they're trying to fly off in straight lines according to Newton's first law of motion, but the wall is holding them in, so they feel like they're walking around the sidewalk. And the artificial gravity field is very simply omega squared r. If multiplied by their mass, it gets the like the full normal force that's holding them in. Okay, I'm going to dig up that clip one more time. Find. Here we go. Okay, here's what it looks like from the outside. Right, goes like that. See it spinning right there. And then if you were inside, it would kind of feel like that. Right now, this is just a movie with special effects, so they weren't actually in space, but that's kind of what it looked like, right? Kind of the idea. Right? Oh, this one last idea, guys. If you climb this ladder, climb the ladder, and you go all the way to the center, what does it feel like the gravity force is at the center, where r is equal to zero? Zero. Yeah. So if you were right at the center and you push off, you just like float up in space. Right, well, pleasant dreams. You guys have a good 3-day weekend.